When you plan to run an organic experiment, usually the easiest part is running the reaction, and hardest part is purifying it, then you characterize it to report. So last week's in the organic labs, we learned recrystallization as a purification method and some characterization methods like TLC, gas chromatography, infrared spectroscopy, and mass spec. And this week we'll learn another purification technique for solid products. It's called extraction. What is extraction? Extraction separates mixtures of different compounds based on their solubility differences in a solvent. In this case, you can extract from aqueous phase into organic phase, or the opposite is possible as well. You can extract from organic phase to the aqueous phase. The main tool in extraction is two immiscible solvents. If you add organic solvent to your coffee, you can extract the caffeine with ethyl acetate, for example, as organic solvent. And after you extract it, you remove the ethyl acetate and you can obtain pure caffeine crystals. I found a video on YouTube just showing how to extract it. It's pretty straightforward. You can watch it if you like to. But in the lab, if you have polar and nonpolar reaction mixture, for example, and you wanna pick only the polar compound and purify it. So what you could do is just get the compounds onto separator funnel, add nonpolar organic solvent. Then the nonpolar compound will dissolve in the nonpolar organic layer, and the polar compound will dissolve in aqueous layer, because the aqueous layer is usually the most polar one, so polar likes the polar one. And the other thing is, how do you know which layer is which? Usually you look for the density of the solvent, organic solvent. So usually the bottom phase is more dense, and that's usually aqueous layer, water. Organic layers are usually less dense, and that forms the top layer. But it depends. If you have halogenated organic solvents, like including chlorine, bromine, they are going to be heavier in density. So in that case, they will be more dense than water, and bottom layer can be organic layer in that case. So you have to check densities all the time for the solvents. I want to highlight the relation between solubility and polarity of compounds. In extraction methods, compounds are separated by their solubility differences in two different solvents. And solubility is a function of polarity. Let's have a general scale for compounds from nonpolar to polar. So uncharged compounds are going to be mainly nonpolar compounds. Look for carbon-carbon and carbon-hydrogen bonds. And they are found in alkanes and most hydrocarbons, so they are mainly nonpolar. When you look for any compound containing electronegative oxygen or nitrogen, that will give some partially charged and partial polarity into the molecules, like in alcohols or amines. So they're in between polarity. And fully charged compounds, like positive or negative charged compounds, such as sodium chloride, that's a salt, and it has charge because of the ionic bonding, and they are highly polar, and they are going to dissolve, for example, in water, because water is the most polar solvent we're going to use. So think about it. If you have something with no charge, like OH and alcohol, so what do you expect? It will be dissolved in organic solvent mainly. So if you can make it having a charge, what will happen? It will migrate into the polar compound category, and it will migrate into the polar layer or the aqueous layer. This is called chemically active extraction, and it is achieved by addition of acid or base to neutral acidic or basic compounds. So in this separator funnel, compound HA, which is acidic, is in equilibrium, so it will be dissolved in organic phase and aqueous phase, but mostly if it's in a neutral form, it will prefer to be dissolved in the organic layer. What if we add sodium hydroxide, a base, to this neutral acidic compound? An acid and base reaction will happen and will produce charged salt and water. And charged species will be more soluble in aqueous layer, so you actually extract the acidic compound into the aqueous layer this way. So this is called acidic extraction. And if you look for carboxylic acids, they are acidic in nature, and when you add the base, you make it charged and it will be water soluble. Then you separate the layer, extract the carboxylic acid, then you neutralize it to obtain the solid form and neutral form again, so it became organic soluble. Similarly, the basic amines can be treated with acids to make a charge for ammonium ion. Then it can be treated with base to neutralize, and then you extract the amines with base, actually acidic extraction. So here is one example again. Let's look at the compounds. You have a benzoic acid, this is a carboxylic acid, and dimethoxybenzene you have. This is an ether. Usually it's neutral, but this one is acidic due to its functional group. And it's dissolved in diethyl ether. Because carboxylic acid is acid, you can do basic extraction to extract the benzoic acid from the mixture. So when you add the sodium hydroxide, the aqueous layer will contain basic charged form of sodium benzoate salt. Salts are charged and became water soluble. And what's left over in the organic layer is the ether compound, dimethoxybenzene, and water. Because you mix organic solvent with water, some water droplets can go into the organic layer as well. So when you separate the layers, you can move on by neutralizing the sodium benzoate salt with HCl. Hydrochloric acid will make it neutral again, and you can obtain solid form of benzoic acid by filtering it and washing it with water, and then dry the solid at the end. I will show a video on how to use a separatory funnel. Here is a separatory funnel. Separator funnel consists of a glass part and a plastic stopcock part to open and close the opening at the bottom. So when you place your separator funnel, you have to place it on this metal ring to stabilize. Then you're going to add your aqueous solution and organic solution. The first thing you should be careful about is stopcock should be perpendicular position. It should be closed when you add your organic solvents to it. When it's parallel, it's open. When it's perpendicular, it's closed. So the first addition is the aqueous layer, which is more dense in this case, and it's pink for visualization. In our case, it will be colorless, maybe. Then organic solution is added. You close the stopcock, and you're going to start securing the stopcock and the cap, then mix it. But never do this one. When you shake it, invert it, there are lots of pressure buildup and towards inside of the hood. Then you have to ventilate it constantly to relieve the pressure inside of it. Don't do this as well, it will cause lots of leaks around the stopcock. So ventilate it until you don't hear any hissing sound or any gas is not coming out. So don't do this kind of shaking. So it's, again, the mixing is like swirling the flask gently, but make sure the layers mix with each other nicely. So remove the cap immediately when you're done and wait for separation of the layers. Here, the separation of the layers are getting much clearer. So you can start your separation when it's a nice line. So first you can collect aqueous layer, which is the bottom layer in this case. When you come to the cavity, you have to slow down because you want this line exactly be at the stopcock level. So you can get a couple of drops at the end, like drop by drop. Then you can collect the organic layer by pouring out into another flask and label that one as well. So your separation is over. Once you're done separation of organic layer and aqueous layer, you have to work up on organic solvents. Usually organic solvents removed by evaporation. But prior to evaporation, there are some residual waters can be removed from the organic solvent by adding a drying agent. For example, sodium sulfate must be added to organic layer. Like in SpongeBob can soak lots of water, so drying agents like acting similarly, absorbing all the water from the organic solvent. So it's an anhydrous inorganic salt and soaks up the residual water by forming a hydrate. They are not soluble in organic solvents and they can be easily separated or removed by filtration. The most frequent question we got in the lab is how much sodium sulfate I should use. I always say add a small amount of drying agent, total like 1 gram per 25 milliliter, and swirl it and observe for clumping. So we have to repeat this until freshly added drying agent no longer clumping. So see here, the first one is not enough because everything clumped together. Here you see still clumping, and you still have like clumps, not free particles floating when you swirl. This one looks good. See, I can see the particles, and when you swirl, they should be free floating small tiny particles. Don't add too much sodium sulfate because it will absorb lots of your product and it will be harder to remove it. So let's finish our example that I gave a couple of slides ago. We did the workup and isolate the benzoic acid from aqueous layer, but we didn't finish the organic layer workup. So benzoic acid is still in organic solvent with some water droplets. You have to add the anhydrous sodium sulfate, filter it, collect the filtrate, which is the liquid part, then evaporate the solvent, in this case is ether, diethyl ether, then obtain solid organic compound at the end. Today's lab, we're going to obtain 3 different samples. They are labeled vial A, B, and C. For example, vial A has 9-fluorinone and benzoic acid. So you're going to obtain it, try to separate those 2 compounds. You will design your extraction procedure that will allow you to separate and recover the two components of the mixture. So I have to approve your protocol before you begin. It must be step by step and clear explanations of each step. Then at the end, you're going to report quantity, how much you recovered from each compound, because each vial containing 1 gram total compound, 1-to-1 ratio, so that makes 0.5 gram 9-fluorinone and 0.5 gram benzoic acid. Then if you get 0.25 benzoic acid, you got 50% recovery. And identity and purity will be evaluated by simple melting point determination. Then you will evaluate if your separation was successful and did you obtain 2 pure products back. So this is another guideline. I would like to kind of help you when you're writing your procedure. So you have the separator funnel, mix it and separated your organic layer. So the organic layer must be dried first with sodium sulfate. So sodium sulfate will clump at the bottom. absorb the excess water. Then you have to gravity filter it into the pre-weighed round bottom flask and remove the sodium sulfate. And the next step, you have to remove the solvent to obtain the solid by rotovap. What is rotovap? It's a rotary evaporation instrument and it's used to remove solvent, and I will show more details when we're using it in the lab this week. It's technically having hot water bath and a cold trap here. You evaporate the solvent, collect the solvent, and then collect the solid product in the flask. So the second part of workup is you have to work on the aqueous layer. If you did the base extraction, you have the aqueous form, the charged acid, benzoic acid, for example. You have to neutralize it because neutralization is exothermic. You have to place it in an ice bath and monitor with the pH paper if it's neutral or not. Then you will see solids precipitating out because when it's neutral, the solid product is not soluble in water anymore, so it will precipitate out. So you want to obtain the solid, then you have to use a vacuum filtration to obtain the solid. Dry it at least for 15 minutes to remove all the water. Then your melting point analysis will be much better.